Hi guys, my name is Sam. I'm a chemistry tutor down here at the Learning Commons, and today I have a workshop on molecular geometry. So molecular geometry and Lewis dot structures, which was the workshop I did previously, pretty much go hand in hand. So I'm going to kind of skip over the Lewis dot structure part. So if we want to know what is the molecular geometry of like methane or CH4, the first thing we would have to do is we would have to figure out what is the central element. So hydrogens are usually, they're never going to be the central atom. There's one carbon, four hydrogens, which means carbon has to be the central atom. So we put the carbon in the middle, and then we draw the four hydrogens around the carbon. And then we draw a bond between each of them. And if we total up the number of electrons, this is 8. Each hydrogen has 1, carbon has 4, which totals up to 8, which means we did it correctly. There's no extra lone pairs or anything. So this is what the Lewis dot structure looks like. But if you want to know what's the geometry of it, we would need, usually the most common way you'll see it is a little sheet like this. We have these down at the Learning Commons. So since there are 4 bonds around the electron, we just look at the sheet, we go down to 4, and it tells us it's tetrahedral. So the actual geometry, it would be like this. We would have the carbon, 2 hydrogens. This hydrogen would be sticking out, and this hydrogen would be going in. And the bond angle for tetrahedral would be 109.5 degrees. So luckily for us, there were no lone pairs on this one, so this one's nice and easy. Now we're going to try one with lone pairs, which is going to mess things up a little bit, because then we're going to get into the molecular geometry and the electron geometry. They're going to differ. So like the common one that people know is water, H2O. Most people know what a water molecule looks like simply because it's just such a common thing to learn about, but either way, we're going to draw the Lewis dot structure. So oxygen is going to be the central atom because there's one of it and there's 2 hydrogens. The hydrogens are going to be bonded to the oxygen. Let me make this a little bigger. And then if we count up the number of valence electrons and then subtract the 4 that we have from the 2 bonds, we know that there would be 2 lone pairs that we need to add. So this is what water looks like, but the way I drew it, it looks linear, which is technically incorrect. So again, we would consult this sheet. This sheet would tell us, the first thing we would look at is the electron geometry. So these electrons are basically going to be little orbitals or shells that poke out. So if we're looking at the geometry between the hydrogens and the electrons, it's going to be tetrahedral, just like the last one, or that's what the sheet says, but we don't really care about electron geometry. The important thing is molecular geometry. So in this chapter, the main theory is called valence shell electron pair repulsion theory, which just means the electrons are actually going to push the molecule down a bit. So again, we consult the chart. 2 bonds and 2 electron pairs around the central atom is what we're looking for, and it tells us that it is bent. So this is what it would actually look like. And then you would have the 2 pairs right up top. And then we're going to do one more example, which is so the main thing you need to look out for is simply you just count the number of bonds and you count the number of lone pairs around the central atom, and then it's just as simple as looking at the chart or memorizing things. So now the next one we're going to do is this one, BH3. So again, we have to figure out which one's going to be the central atom, and it's going to be the boron. There's going to be, obviously, the 3 hydrogens are going to be attached to the boron. And if we count up the number of electrons, the number of valence electrons, boron has 3, and each hydrogen has 1. So this will be a total of 6 electrons. So that's 2, 4, that's 6. So again, the way I drew this is technically incorrect if we look at the molecular geometry, because this looks like it's T-shaped. But if we consult the sheet again, there are 3 bonds around boron, and there are no lone pairs. So again, you can just look at the sheet, and it tells us it's trigonal planar. So it would actually be like a triangle with 3 hydrogens around it. And the bond angle between these is going to be 120 degrees. I'm actually going to do one more example, because one other thing that can throw you off whenever you're drawing geometry is double bonds or triple bonds or something like that. So we're going to do the common example of a double bond molecular geometry, and that's CO2. So here's the last one. CO2, carbon dioxide. So carbon's going to be the central atom. We're going to put carbon in the middle, and then we're going to put oxygens on the outside. Now, if we total up the number of valence electrons, oxygens have 6, so that would be 12. Carbon has 4, so that would be 18 valence electrons. So the first thing we're going to do is we're going to try it this way. We're going to bond each of the oxygens to the carbon 1 time, and then put our valence electrons around the oxygen. But this is a total of 16 electrons, which isn't enough for carbon to have its octet, which means there's no reason why carbon would bond this way. So this is incorrect. This is an example where you have to put double bonds in. And again, this is really more on the Lewis dot structure side, so I'm just going to draw what it's going to look like. So the carbon is going to have 4 bonds around it. Each of the oxygen is going to have 2 bonds and 2 lone pairs, which means they all have their octet. Now, you might think that this is 4 bonds around the carbon, so it's going to be tetrahedral. But each double bond essentially just counts as 1 bond whenever you're looking at molecular geometry. So if carbon has 2 bonds around it, that means it's linear. And again, this sheet has the valence shell electron pair repulsion theory on one side, and then it has the valence bond theory, which deals with like triple bonds and double bonds and how they affect the geometry. So this would be linear. It would be 180 degrees. And that pretty much sums up the theory behind molecular geometry. You just have to count the number of bonds, count the number of lone pairs, and then consult the chart. And do we have any questions? Nope. Okay, well, if anyone has any questions on their finals, we'll be here on the Learning Commons all week, and good luck, guys.